All right, let's dive in. Today we're talking about Apache Spark, the open source engine that completely changed the game for big data. We're going to explore how it took the world by storm, and it did it by totally rethinking the architecture for speed, for ease of use, and for unified analytics.
But to really get why Spark was such a big deal, we have to go back to the beginning. We need to understand the problem it was built to solve. And that story starts with its predecessor, a true giant in its own right that eventually started to creak under the pressure.
So let's talk about the original king of big data, Hadoop MapReduce. For a long time, it was pretty much the only game in town for processing internet-scale data. But as data science started to get more sophisticated, the cracks in its armor really began to show. And here we go. This is the core of the problem with MapReduce. Just look at all those disk operations. Nearly every single step of a job meant a slow, painful round trip to a physical hard drive. It would read the data, do some processing, and then immediately write the results right back to the disk, only to have to read them all over again for the very next step. All this constant disk I/O made MapReduce just incredibly clunky for the new kinds of work people wanted to do. I mean, think about machine learning, right? You're running the same algorithm again and again on the same data set. Or interactive analysis, where a data scientist wants to ask a bunch of quick questions. For these modern jobs, MapReduce was just too slow.
So clearly a new approach was needed, something that could break free from the shackles of the disk and bring all that computation into the lightning-fast world of computer memory. And this, right here, is where Spark enters the picture.
Okay, so the absolute heart of Spark is this concept, the Resilient Distributed Dataset, or RDD. The easiest way to think about it is like a normal collection of data, maybe like a list. But this list is spread out across the memory of many different computers in a cluster. It's immutable, which means you can't change it. And most importantly, it's resilient.
So how does Spark get that resilience? Well, instead of copying all the data itself, which is super expensive, Spark keeps track of the lineage. That's the exact sequence of operations, the recipe, used to create that RDD in the first place. So if a machine in the cluster just dies and its piece of the data disappears, no big deal. Spark just uses that recipe to rebuild the missing part on another machine. It's a really brilliant way to get fault tolerance without all the overhead. This also brings up another one of Spark's secret weapons, something called lazy execution. See, when you tell Spark to do a transformation, like filter this data or map over it, it doesn't actually do anything right away. It just adds that step to its to-do list, its execution plan. It's only when you call an action, like count, that Spark looks at the entire plan and figures out the most optimized way to execute the whole thing at once.
Okay, now let's see how this core idea of in-memory RDDs was blown up into something much bigger. Because Spark isn't just a faster MapReduce, it's a complete unified ecosystem for all kinds of data work.
You see, built on top of the Spark core engine, the part that handles all the RDDs and job execution, they built this whole suite of powerful libraries. You've got Spark SQL for running standard SQL queries, Spark Streaming for processing live data, MLlib for machine learning, and GraphX for graph processing. And the key is, they all run on the same engine and they all work together seamlessly. Spark SQL, in particular, was a huge leap forward. It introduced this thing called data frames, which are basically RDDs that have a known structure or a schema. With a plain old RDD, your code is just a black box to Spark. But with a data frame, Spark actually understands the structure of your data, and that lets its internal optimizer go to town.
And that magic is called the Catalyst Optimizer. When you give Spark a SQL query or a data frame job, Catalyst takes it and transforms it through all these different phases. It analyzes it, it applies a whole bunch of smart rules, like pushing filters down to the source, and then it generates the most efficient execution plan possible. It's this incredibly sophisticated process that just happens automatically, behind the scenes.
So we've seen how Spark can crush massive static data sets. But what about the real world, right? Where data never stops flowing. How does this engine that's built for batches handle a live, never-ending stream of data?
Well, the approach is both really simple and incredibly powerful. Instead of trying to process records one by one as they come in, Spark Streaming just chops up the live stream into a continuous series of tiny, discrete batch jobs. Think of it as taking a snapshot every second or so.
This sequence of little batches is called a discretized stream, or a D-stream. And here's the beautiful part. Each one of these tiny microbatches is just a normal RDD, which means you can use all the same powerful tools you already know, map, filter, reduce, but now you're applying them to live data. It totally unifies the logic for both batch and stream processing.
Now, to manage these incoming data fire hoses, Spark Streaming is very often paired up with Apache Kafka. You can think of Kafka as this massive, scalable, and super reliable buffer. Data producers write messages into Kafka, and Spark, as the consumer, just reads from it at its own pace. It decouples the two systems, which is great because it stops the data source from ever overwhelming the processing engine.
All right, let's explore a classic streaming problem that, well, it seems pretty much impossible at first. Imagine you're processing a huge stream of user IDs and you need to filter out any user you've already seen today. How on earth do you do that when you have billions of users and you can't possibly afford to store a list of every single ID you've seen in memory?
The solution is this really elegant, almost magical data structure called a Bloom filter. It's so clever. You start with a big array of bits all set to 0. When you see an item for the first time, you run it through several different hash functions. Each of those functions points to a position in the bit array, and you just flip that bit from a 0 to a 1.
So here's the payoff. When a new item comes in, you hash it the same way and check those same bits. Now, if even one of those bits is still a 0, you know with 100% certainty that you have never seen this item before. It's definitely new. If all the bits are 1, well, it's probably in the set, but there is a tiny chance of a false positive. For filtering out new items in a huge stream, this is an unbelievably memory-efficient tool.
So, let's bring it all home. With all the new tools that have popped up since, why does Spark remain such a dominant, important force in the world of big data?
Well, first and foremost, you just can't argue with the raw performance. By moving computation off of slow-spinning disks and into fast system memory, Spark gave us this monumental orders of magnitude leap in speed. For a lot of jobs, especially the iterative ones, this meant going from waiting hours to just waiting minutes.
But honestly, speed is only part of the story. Spark's true, lasting legacy is unification. It gave everyone a single, cohesive platform for a whole range of tasks: batch jobs, SQL queries, real-time streaming, machine learning, that used to require you to stitch together this complex, messy patchwork of totally different systems.
This quote really just nails it, doesn't it? It successfully brought together those three crucial things: speed, being easy to use, and having real analytical power, all into one engine that just empowered a whole new generation of data engineers and data scientists.
And that leaves us with a final question to chew on. Spark's biggest achievement was bringing a unifying simplicity to the chaotic world of big data tools. So what other complex tech landscapes, maybe in AI or cloud infrastructure, or even front-end development, are out there right now just waiting for their own unifying force like Spark to come along?